All right, we are ready again. And I want to make one quick correction, as Mark pointed out. Today's talk by Mark Harris is going to be specifically on unified memory in CUDA 6. So with that, Mark Harris with Nvidia.
Thanks, Allison. Hi, everyone. Thanks for coming this morning. I'm going to talk to you about unified memory in CUDA 6. If you're interested in other features in CUDA 6, I recommend you come tomorrow, I believe at 1 p.m., where I'll talk about more features of CUDA 6 and less detail about unified memory. So unified memory is one of the most dramatic changes to productivity that we've had in CUDA in its history. This slide shows you a pictorial view. So if you look at the left-hand side, it shows you the view of, or actually it shows you the architecture of a heterogeneous system where you have two processors and two discrete physical memories. And today in CUDA, this is exactly how the programmer views it. The programmer has to manage allocations in both memory spaces and explicitly copy data between them. With unified memory, we allocate a shared or a managed pool of data that bridges the divide between the CPU and GPU. And the runtime handles automatically migrating data between the physical memory spaces to where it's needed. So the result is that it greatly simplifies the code you have to write to manage data for CUDA programs. So these two programs do the same thing. On the left you have CPU code, and on the right CUDA code. On the left, the CPU code basically just allocates memory with malloc. It reads data from a file into that allocation. It sorts it using qsort. And then it uses the data on the CPU before freeing the memory. On the right, we have the CUDA 6 version, where the only change is that we sort the data using a parallel kernel, and we allocate the data using CUDA malloc managed. CUDA malloc managed is a new unified allocator in CUDA 6, which allocates data in this managed pool. So now we can allocate memory on the GPU that's migratable between the GPU and the CPU. So we can pass that pointer directly to CPU functions. So we can pass the data pointer to fread and read from a file directly into it. And then we can launch a kernel, and the data that we loaded from the file is automatically migrated to the GPU so that the kernel can access that memory at full bandwidth. And then after we synchronize the GPU, we can use the data again on the CPU. So this makes it very simple to get straight to writing the parallel parts of your code, because you don't have to do a lot of extra allocations and explicit memory copies between the CPU memory and the GPU memory. Unified memory delivers in two areas for programmers. The first is simplifying the programming and memory models, as I've described. You now have a single pointer to your data that's accessible anywhere. So this more tightly integrates the languages. The language, you use the same language and the same data to program the CPU and the GPU. And that greatly simplifies code porting, and I'll show you some examples of how, by allowing you to share complex data structures between CPU and GPU code. Second is in performance through data locality. The CUDA runtime now migrates data to the accessing processor on demand. And by doing that, we make sure that when we access the data on the GPU, we're doing so with the full GPU memory bandwidth, rather than accessing it remotely over PCI Express, for example, which is another way to share data between the CPU and the GPU. And it also guarantees global coherency at the time of kernel launches and at device synchronization. Now, you can still use all the tools that are available in CUDA today for optimization. So you can use CUDA memcopy async, and if you carefully tune overlapping of data transfers and computation, you may be able to get higher performance than automatic managed memory. But now these memory copies are an optimization rather than a requirement. So it's easier to get started, it's easier to port your code, and then you can move to tuning it. Let me show you an example of how unified memory simplifies coding in CUDA. here we have a data structure. It's a struct that has two integer members and then a char star, so a pointer to string data. If we want to allocate that and initialize that on the CPU and then pass it to a GPU kernel, then we have to do three copies, really. We have to copy the struct itself, and we have to copy the string data, and then we have to copy the pointer so that we make sure that the pointer in the GPU copy of the struct points to the GPU memory we allocated rather than the CPU. And this is known as a deep copy. And deep copies today result in very complex code just to launch kernels on the GPU. So this makes it difficult to share data structures between the CPU and the GPU. So here's the code for this. You can see we have two allocations of the struct on the device and the string on the device, and then we have to copy the struct, we have to copy the text, and then we have to copy the pointer to the text. And then, only then, can we launch the kernel. Well, with unified memory, of course, if we allocate all this data in unified memory, then either the CPU or the GPU can access it from a single pointer, and we just have to launch the kernel. We don't have to do any explicit copies ourselves. The CUDA runtime manages that for us. Another example of this is the canonical computer science data structure, the linked list, which is essentially a structure like the one on the previous slide where each element is pointing to another element. And so we have lots of these nested pointers. And the problem, well, the only real way to do this before unified memory in GPU computing in order to share a linked list between the GPU and the CPU is to just leave it in CPU memory and access it, allocate it as pinned host memory, or what we call zero copy memory, where the GPU kernels are able to directly access the CPU memory. But those accesses are all done over PCI Express, which has much lower bandwidth than the GPU's memory and much higher latency. So performance suffers. But with unified memory, we allocate that in the managed space, the whole data structure, and now we have a single linked list that we can share between the CPU and GPU. We can access elements from either processor. We can insert and delete elements from either processor. And we just have to make sure we don't have race conditions between them. Unified memory really shines with C++. And I'll do a little bit of an in-depth example here. But the problem with C++ without unified memory is that non-simple data structures that have have non-default constructors don't know how to allocate GPU memory. And so you can't automatically share those between the CPU and GPU, because if we create one of those this structure and then we pass it by value to a kernel, then that's going to call a copies constructor, and we're only allowed to have a default copy constructor, which means it won't allocate any data on the GPU. And so the result is that we don't actually have any valid references to access memory. But unified memory solves this. The nice thing about C++ is that we can overload the new and delete operators, and we can implement them so that they use the managed heap. So we can use CUDA malloc managed in the new operator and CUDA free in the delete operator. So here we define this utility class called managed, and it defines new and delete. And then we inherit from that managed class in classes that we want to use unified memory, or that we want to share between the CPU and the GPU. So here we have a string class that has char star data and the length, and we inherit from managed, which means that when we call new, it will allocate unified memory, and when we call delete, it will free it. Now, we can also, so that enables pass by reference. If we want to be able to pass these by value, then we need a copy constructor. So all we do is we create a copy constructor, and we use CUDA malloc managed in the copy constructor to allocate space for the copy that we're creating. So now that we've done that, we can now create our data element class, which has a string. So here I'm using the string class rather than a char star. And we also have to make sure that we inherit from managed in that so that it's allocated in managed memory. But once we do that, we can just use new, as we do with anything in C++, in the CPU code. And so if I say new data element, it allocates the data element and the string data in unified memory. And then I can use pass by reference and pass by value without any extra memcopy work. It's all done inside of the C++ utility class and the copy constructor that we wrote. So now we can define a kernel that takes a reference parameter. And this is actually new in CUDA 6. Before CUDA 6, we didn't allow reference parameters to kernel functions. We can define a kernel that has a reference parameter, and then we can call this kernel with pass by reference to the data structure that we allocated in unified memory. And since the GPU and CPU can both access that data from a single pointer, it just works. And if we want to instead do pass by value, we can define our kernel to use pass by value parameters. And what will happen is we'll invoke our copy constructor. In the case of the data element struct, it's going to use the default copy constructor. And then that will invoke the strings copy constructor that we defined explicitly. And we get a copy created in managed memory. And then the GPU will access that copy. So those are my examples. I hope that demonstrates to you the benefits of unified memory in terms of the ease of porting existing code and the ease of getting started with writing applications in CUDA C and C++. But the nice thing about unified memory in CUDA 6 is that this is just the beginning. We have a whole roadmap planned for improvements. So with CUDA 6, you get a unified allocator, CUDA malloc managed, that provides a single pointer to data. So it's accessible between the CPU and GPU without a memcopy. You have coherence at the time of kernel launches and at synchronization. And this means that you can now share complex C and C++ data structures between host and device code, as I've shown. In the next releases of CUDA, we plan to add optimizations which will make unified memory faster. Those include automatic prefetching and migration hints to provide the programmer with some control over telling the runtime how it should manage the data and where it should keep it at certain times. I should have mentioned that in CUDA 6, unified memory is supported on 64-bit Linux, Windows 7 and 8, and we'll be adding additional operating system support in future releases. And then when we get to our next generation Maxwell architecture, it will have built-in support for unified memory, which means that we can unify the system allocator. So what that means is that you can use malloc or default C++ new, and any data that you allocate with that is unified, and so it can be accessed by either the GPU or the CPU. And that also means that stack memory is unified rather than just heap memory. And finally, hardware-accelerated coherence will overall improve the performance of unified memory even more. I'll just give you a taste of CUDA 6 in case you don't get a chance to see the CUDA 6 talks. Unified memory is probably the most important feature in CUDA 6, but there are a number of other really exciting features. We have new library interfaces that provide multi-GPU scaling and drop-in replacement for host BLAS and FFTW interfaces so that you can easily accelerate your FFT and BLAS level 3 operations on GPUs without writing custom allocations and calls to a new library. GPU Direct RDMA and MPI. OpenMPI and MVAPage 2 will be supporting GPU Direct RDMA, which allows direct access to data between GPUs on different nodes across InfiniBand on top of the Mellanox stack. And that reduces latency inside the node in MPI transfers, which can lead to better scaling. And finally, we have a heap of improvements to our developer tools. We have remote development tools in Insight Eclipse Edition so that you can run Insight locally on your laptop and profile and debug an application running on a remote machine. And we have more detailed insight in our profiler, as well as support for profiling and memory checking on our multiprocess service. Okay, so that was an overview of unified memory in CUDA 6. If you'd like to learn more, I recommend you check out a blog post that I wrote. The URL is there, or you can just Google for Parallel for All, and you'll find it. And if you'd like to find out early when the release candidate of CUDA 6 is available so that you can try it out, I recommend that you sign up for our CUDA Registered Developer Program. Okay.
Great.
Thanks.
Thank you very much, Mark. And we have time for some questions, if you have any questions of Mark.
Yeah, you showed the unified memory handling like linked lists and things like that. Does it seamlessly handle circular data structures, complex data structures, things like that?
Well, it's just memory. It's migrating memory pages. So, yeah.
When you use the managed memory runtime, are there like hints you can provide for when you're going to use data on a GPU versus a CPU to kind of do some prefetching, or is that something that if you really want to fine-tune that, you're going to have to use the kind of old-style explicit copies themselves?
So in CUDA 6, there aren't any hints. As I mentioned, we do have plans in the next releases to provide migration hints. I will say that if you're a skilled CUDA programmer, or if you have an existing code that's already tuned to use asynchronous mem copies, overlapping computation and data transfers, then you're probably already running faster than you would with unified memory in CUDA 6. But it can help in some places where you have sparse access and you don't know what bytes you're going to touch ahead of time. So.
Do you track modified pages on the GPU so you know what to copy back, or does the entire heap get copied back at the end of the...
We keep track of modified pages. Yeah.
What memory size constraints do you have?
So in CUDA 6 on current hardware, I should have said that this is supported on Kepler hardware, so CUDA compute capability 3.0 hardware and later, it's limited to the size of the memory of the GPU.
Okay. And if you're going to be running multiple kernels, is it smart about what to bring over for each invocation, or does it bring over the entire malloc space, managed malloc?
I believe it's pretty smart about moving the data at the time of kernel launch or before the kernel launch that kernel touches. And what's basically, where's Steven? There he is. Is that right? That's right, right? Yeah.
How does the unified memory deal with page sizes?
How does it deal with page sizes?
Yeah, in Linux, so you might have a memory page size a certain block, and how does it, does CUDA unified memory use the same page size as the Linux page size?
Yes. Do I need to give more detail on that? Yeah.
I was wondering, can you synchronize on a specific malloc unit?
Can you synchronize on a specific unified or managed allocation?
Yeah, managed allocation.
Well, let me see if I get this right. You can attach a managed allocation to a specific stream and then synchronize that stream. I think that would give you some fine-grained control over that. Yeah, there's an API that I didn't go into that allows you to associate an allocation with a stream.
So actually what you just said might answer this, but I was wondering about dealing with unified memory across multiple GPUs in the same application. So you have a single managed address calling into two kernels on two different GPUs. Is there a reasonable way to handle the copy back?
The copy back to the other GPU?
No, I mean from both GPUs to the host. Say they each touch half of one page.
I think that's handled for GPUs that support peer-to-peer, that are compatible with for PCI Express peer-to-peer communication. Is that right? Yeah. If they're not, like if you have different GPU models that don't support peer-to-peer communication, then I believe it falls back to zero copy memory, and so it's all in the host memory anyway, but it's slower.
Could you hear that?
I heard it. He said,
you
so that
repeat it
means
for
that
the-
means anything with more than one I/O hub breaks down, and I'll let Stephen answer that.
And I don't want to neglect our online community.
Okay.
So we have a question here. Will the next version of Insight show the memory transfers happening in unified memory?
That's a great question. And it's something I should have mentioned. The tools in CUDA 6 are unified memory aware, so you can profile a unified memory application and see the individual migrations that are happening. So,
Great. Any other questions for Mark? Well, with that then, thank you again, Mark.
thanks for coming, everybody.